Hi, hi to everyone. Okay, and I will share the screen. Okay, so um, we saw last time that what we saw last time was that the small PRG implies a PRG forever, and it is an important construction because that's how stream ciphers work. And it gives you the intuition that a small little thing can be hooked up and create this useful service, production of a continuous production of a pseudorandom string. For example, for the stream cipher for the application of encryption, without knowing how long, while keeping it can go forever basically, and it only keeps a small state. It doesn't need to know where it was, how far it went already, or how far it will go in the future. But more philosophically, what you are learning is the kind of method for arguing about security where you can reduce adversary behavior, distinguishing this continuous operation of the polynomially many rounds of this little cipher, little PRG, versus completely random string for megabytes or gigabytes or whatever, right? Any polynomial. And how do you abridge between the two and reduce security to security of this little building block that was operating at every round? And it's this hybrid idea that you take your complicated computation and somehow analyze, in some sense, like a reduced operation of it. So at every reduction, this computation gets smaller and smaller. And well, in this case of analysis, the rest is just filled with random noise. And if somebody can tell two endpoints of this, then they must be telling beginning and end of some step. And then you reduce to security of the underlying block. We'll see this again today, and we'll see this again and again. So I want to talk about the equivalent formulation of what a PRG is in terms of next bit unpredictability of its output. Okay, so we defined what is a statistical test. So let me just go like this. Remember, we defined what a statistical test is. What is an attack against a PRG? It's a statistical test, meaning it takes a string and it tries to decide what about that string is not random. It's not fully random. It cannot be fully random if it was all created from a short entropy and expanded by this deterministic algorithm. So the long string can possibly have only the amount of entropy that the seed had. There must be correlations. That's what the statistical test does. It tries to figure out these correlations. We said that the PRG is secure if its outputs, it's impossible to find any correlations by an efficient algorithm, by an official statistical test cannot distinguish this from a fully random string. But here is an alternative definition, and just as useful, just as intuitive. The test doesn't take the whole string. The test takes, the tester takes the output of a PRG up to certain index. Okay, so up to bit I. Think of a stream cipher which operates. perhaps encrypts using right stream cipher with some messages, but perhaps adversary knows what these messages were. So because he knows what these messages were, so from ciphertext, he immediately gets the PRG output until this index. And any hypothesis of what the messages are gives you, you just XOR with the ciphertext and you get a, okay, so how about this being the first I bits of a PRG? The question is, if you knew these messages, so you knew these outputs, can this tell you anything about the next output, right? So say you knew what messages were, he encrypted a bunch of IP packets and you knew them all. They were standard IP packets, like everybody gets these. But then IP packets that you don't know. So because stream cipher was in operation, so you learned all these outputs of a PRG. Could they tell you anything about the next chunk of output of the PRG? And here, this notation is, I take a bit string and I chop it, and here I tell you at what indexes. So I just take this bit string and I say, this is the substring that goes from first to ith bit of this one. And this one is just, I'm looking at the I plus first bit in this string. Okay, it's my notation. Okay, it's like, I guess the better would be an open bracket and from 1 to I, and here an open bracket and I plus 1. And we say that the I plus first bit is predictable if there is some efficient adversary which predicts it, which outputs it. And we don't ask that it's for sure true, but we ask that it's significantly different from just guessing at random. So he is a successful predictor if this probability is 1/2 plus more than negligible. Okay, so let epsilon be this non-negligible advantage. So, okay, so this is just, and conversely, we say that the PRG is unpredictable if this advantage is just 1/2 plus negligible amount. So with every efficient tester, when he's getting the first I bits of the G in output, it's useless to him. He predicts this bit with the probability that is effectively the same as random coin toss. Okay, plus like a negligible, okay. And I am not stating this here, I just realize it is not predictable if this is true for all indices. So it's not predictable, like the 11th bit is not predictable from first 10. 20th bit is not predictable from the first 19, and on, right? At no index, you can feed the previous bits to some algorithm and he is going to predict the next with probability better than just guessing it, completely flipping the bit. So that seems a pretty intuitive notion of what we would like of a PRG, right? A PRG indeed must be such that, well, this example with the attack on a stream cipher, right? Where if I know the first I packets that this guy encrypted, it should tell me nothing about the next one. And indeed, if a PRG was as good as if it had a random string, then that is true, right? Like you split the random string, completely random string into first I chunks. They tell you nothing about the next chunk of a completely random string. So if it was true that PRG outputs are as good as random strings, then they are unpredictable. Okay, let's hold this intuition. And let's see what is the difference between these two notions. So here is the PRG notion. It said that every efficient statistical test, when you see how he behaves on outputs of G on a random seed, you feed him these G produced strings in their entirety. and he acts certain way, he outputs a 1. And then you compare it to the way that he outputs the same output, but you give him a fully random string. PRG is secure if for every such test, this is negligible. PRG is unpredictable if for every test that just sees the first I bits, he cannot predict the I plus first. Are these two notions equivalent? Which one follows from which one? Okay. So I was kind of hand waving that it must be that if the PRG notion basically says that a PRG is as good, PRG outputs are for all applications as good as random strings. If somebody gets PRG outputs, they cannot distinguish them from random strings. So any experiment performed on this PRG output can be replaced by an equivalent experiment where PRG output is replaced by a fully random string, and this alternative experiment will behave the same way, or at most negligible difference it can create. That does imply unpredictability. Okay. Yeah. Okay. So I'm just repeating myself. Question is, why not the other way? So this is the easy direction. If a PRG is secure, then it's also unpredictable. Let's show it formally by counterpositive. That if this was violated, so there was some predictor, then the assumption must be violated. So that means that it cannot be a secure PRG. In other words, if we have a predictor that has an efficient algorithm that given the first I bits of an PRG output predicts I plus first, then we can build or use this predictor to build a distinguishing attack on a PRG. In other words, contradict this, right? So just conclude that PRG is insecure. Okay, so this is just counterpositive versus positive. So now, yeah, I mean, this is like in case you were not convinced that what I'm doing here is really a counterpositive of what this says. So let's say that there is an attack that violates this notion. So it is so in other words, it's an attack against prediction. So there is some index I and an algorithm A that given the first I bits of a PRG output, predict the I plus first with probability 1/2 plus non-negligible. So reduction that shows that this PRG cannot be a secure PRG. In other words, a reduction that is going to perform a standard attack on a PRG. What is the standard attack? This reduction, I'm going to call it B. What is the standard? I mean, how to show that B? How to construct B that violates PRG, that shows that PRG is insecure? Well, this X is either a PRG output or a random string. B should use A and somehow use this to basically distinguish between X's that are random strings and X's which are outputs of G. Okay, let's see if that succeeded. So first, what does B do? So it gets this random string, and it has this A who says that he predicts I plus first bit given the first I. Okay, so give him the first I bits of this string and see if he predicts. If he predicts, outputs 1. If he doesn't, output 0. Very strict, very clear procedure for how the reduction should use this guy, A, to attack the PRG. Let's first see, so the procedure is clear. This B guy given an X is a clear code, how B behaves. Let's see now is this B a successful attack on a PRG? So there are two cases. We have to look at what happens when X is a random string, and what happens if X is G of K for a random K, from a random seed K. Yeah, so these are the two cases. So let's first see what happens when X is this random string R. So B gets a random string R. It feeds a random string, the first I bits of a random string to A, and then measures the probability that A guesses the I plus first bit of string R. But because it's a random string, this bit is completely unrelated to these, right? Random string means every bit is chosen fresh. So this bit is 1/2 probability that, so regardless of what A does, the true I plus first bit of a random string is going to equal to this output with the probability exactly 1/2, regardless of what this A does. I mean, unless A outputs something that's not even a bit. Okay, but as long as A outputs a bit, then this is true, that A's output equals that random bit with probability 1/2. So therefore, B is going to output 1 with probability 1/2. Okay. And now look at this case. B's output is GK. So what that A gets is it gets the first I bits of GK, and we are outputting 1 if A predicted the I plus first bit of GK. That is exactly what we called epsilon, right? So the assumption was that that this probabilistic statement holds with the probability at least 1/2 plus epsilon. This is exactly the statement that is here happening here, right? Because B outputs 1 even only if A of first I bits outputs the I plus first. So this guy is exactly 1/2, and this guy is 1/2 plus epsilon. So the difference between them is epsilon, right? I mean, this is bounded above, so it's bounded above. Okay, so any questions about this reduction? You could structure this reduction differently. You could, for example, well, first of all, you could output 0 here and 1 here, right? This would not change. You could also, in the other case, you could like flip the bit at random. It would just, the only thing that would happen, it would complicate the analysis. If you flip this bit at random, then there will be like one more, the probability here will be 3/4, and the probability here would be, basically 3/4 plus epsilon, maybe divided by something. So it would just complicate it. It would still work. This is often the case when you are trying to solve such a problem, like for example, problem 3 on the homework. You will, in problem 3, you have an attacker that, no, in problem 4, I think, you have an attacker that attacks the PRG, and you want to build an attack against encryption or vice versa. I forget. But you can do it in a way that makes the reduction very easy and makes the argument easy. If you might do it in a way that just makes this argument more complicated, but it's still, you can make it. The same, by the way, holds for problem 3. You show an attack against some notion, and but the attack is not very efficient or doesn't have great advantage. But nevertheless, you're building this attack, and to analyze what its advantage is? Well, one way you do this attack might be make it easier to analyze it. And a slightly different one suddenly makes the analysis more complex. Think about this, because as you make the attack, you think that this is attack. Okay, this is your first guess. And then the analysis, you're not quite sure. Okay, maybe instead of working hard on this analysis, maybe modify the attack so that the analysis is simplified. So you have more freedom. You don't have to be stuck on one path. Perhaps change something. Perhaps, don't try. Sometimes the mistake is, be very, very correct, like squeeze as much power as possible. But actually, this version of an attack is hard to analyze. Make it as simple as possible. Perhaps you can still analyze it, and in fact, then it will be easier. Okay. So the other direction is harder. The other direction is that, okay, what we have shown is that if it's secure, so if the whole output is pseudorandom, then there cannot be a test, a predictor test at any index. What about the other way? That let's say that we know that there is no predictor test, that this scheme is unpredictable at every index. Does it mean that the whole thing is indistinguishable from a random string? Okay. Yao sort of proves that that is the case, but it is not an immediate proof like the other one. So what he showed is that basically if there's no if the next bit predictors fail, then there cannot be a statistical test. In some sense, so this was progress, because an attack on a PRG that is, you see, the way stream cipher works is that we don't know how to wait for the whole string. It actually does not have limits. I mean, it's polynomial time, but like who says what? I don't have to fix the polynomial at the beginning. So you don't know how long I'm going to run really. And that's not an attack that happens in practice, right? Like there's, okay, so somebody is listening to everything somebody else said, and they know everything that they encrypted, then they get the full string. But in practice, you get chunks. You get the stream cipher for some time. And it's a question, can you use that to predict the rest? So if you, what Yao's research says, if you focus your analysis on showing that this next step prediction cannot work, then the whole thing is a PRG. Let's see. So because we're going to go by counterposition positive again, so that's the technique we essentially stuck with throughout the class and the field in general, is that, okay, so let's assume there is an attacker against that distinguishes the full output from random. No. And now let's build an explicit predictor that, given the first I bits, predicts I plus first. But where is I? Well, we must show that there is some I, such that if you see the I bits, then you can predict the I plus first. And you can see that there is a problem in this. So let's say that you have this algorithm A who attacks the PRG. right? No, sorry, B, sorry. B distinguishes outputs of G from random strings. Then let's find this efficient predictor that given the who's given the first I plus, who predicts I plus first bit given the I bits. So the algorithm B breaks the PRG. So there is a probability with which he acts on a output of a PRG, and a probability P prime how he acts on a random string. And let's assume they are sufficiently different. So P minus P prime is a non-negligible epsilon. Hold on just a second. Zosiu, Ester dzwoni do mnie. So how can we use B to construct A? Okay, B has all the bits of the output. And once it has all the bits, then it distinguishes this from a random string. So perhaps we can build a predictor that has all the bits except of the last and predicts the last bit based on how B does, what B does. Well, what is A's input? It's n minus 1 bits. And these are outputs of a PRG, actually. And the only thing A has to do with these bits, I call them S here, is that it has to predict the last bit. But the only thing it can work with is some algorithm B that takes all the bits. Okay, so what can we possibly do? Well, run B on these n minus 1 bits concatenated with 0, and run B with n minus 1 bits concatenated with 1. And perhaps if he outputs, so we assumed we were measuring how well he, the probability that he outputs 1 on a PRG string, and the probability that he outputs 1 on a random string. And on a PRG string, he answers 1 more often. So if you feed him a string and he gives you a 1, that's like a vote that this is more likely to be a PRG output, right? That's the correlation that B promised. So if basically you see, does he output 1 on this? Does he output 1 on this? And I guess on the one that he outputs 1, then you take it as a vote that this is a correct PRG output. And so you output that bit. But there are, so of course, many problems with it. First of all, what guarantees that he doesn't both output 1 on both of them? Then you still don't know, right? Which one is correct? Well, but can you, that's not yet doesn't show you that this attack doesn't work. So maybe if he outputs 1 on both, then you flip a coin and you just predict this bit at random. You give up. And if he also gives you 0 on both of them, then you also take at random, right? But if his advantage is towards answering 1 on correct strings and 0 more on incorrect ones, then probabilities will still work out. If he on these, if he, one of these things will be correct. One of these will be a PRG output. The other will be a PRG output with the last bit flipped. So perhaps he does, he will, using him will give you an advantage. But basically, no. Because statistical test gets all these bits. Who says that the statistical test even looks at the last bit? Perhaps it correlates other bits and never looks at this last one. So the B does distinguish fully random string from a PRG output with advantage epsilon, but a PRG output which is correct versus PRG output with the last bit flipped, this B does not distinguish because this last bit is not what he looks at. Well, but you can continue this and say, okay, well, if he doesn't look at the last bit, then I can recurse and do this perhaps at a one less index and feed him with all sort of suffixes filled in here because I have to fill him with all n bits. You again, even if you say, okay, like that, let's say that he doesn't look at the last bit, and let's say that we can even say that, although it's not clear what does it mean that an attack doesn't look. But I guess we could specify what it means. It means explicitly that like seeing PRG outputs versus PRG outputs with the last bit flipped, it behaves the same way or negligibly close. Okay, we can try to work with that class of attackers and try to run them on these strings. And I guess because he doesn't look at the last bit, so maybe provably we can ignore, just forget about this string and forget about this one. Just run it on two different strings that only differ on the n minus first bit. So perhaps you can make an argument from this type of recursion, but it will be complicated. It's here's an idea that that does work, and it basically cuts to the chase. Show that there exists an index such that the following reduction works. The reduction is getting the reduction A. Again, the goal of A is to show a prediction at some position. So this A will predict at the position I. So he gets S, which is the first I bits. Then he I think guesses this bit B at random, or perhaps runs twice, first for B0 and one for B equal 1. But the remaining bits are random. And if it was what we want is that B on these type of inputs acts significantly different, so significantly more likely to output 1, then B, where the first I bits are the same, the I plus first bit is flipped, so it's an incorrect bit of a PRG, and R is again a random pad. So all the subsequent bits are just random. If we knew that B acts this way at some index I, then we could use him as in a reduction. The reduction would take S, run B on this string where R is random and B is, let's say, pick 0, run him on this string where R is random and now B is 1. I mean, this bit is 1. And or you know what, it will run him once with a random bit, see if he outputs 1. If he outputs 1, then then the reduction, which attacks the unpredictability notion, will output bit B as the next bit of a PRG. And if he outputs 0, then it will output a flip of bit B. So This is what we need, that there exists an I like this. And maybe not surprisingly now, we will do this by a hybrid argument. So we will show that no matter what B does, there must exist this index where this is the case, where this is different. The way he acts on strings like that and strings like that is not negligible. Okay, so yes, so I have this reduction here. A given an I bit strings, picks this bit at random, fills in the R's, and if this B outputs 1, then it outputs B, and if B says 0, then it flips it. Okay, so let's see how why this is true, and this is true by the hybrid argument. So we took algorithm B, which given PRG given purely random strings. Oh, sorry, I flipped P and P prime from last slide. Sorry about that. So here on this slide, I have P, which is purely random, how B acts on purely random, and B prime, how he acts on PRG outputs. I will stick with this because it will be consistent within the slide. So I want to show that there is an index such that if I feed this B with a different distribution, the GK outputs at I, then B, and then purely random. Then it outputs 1 more significantly than if I feed him the same distribution, but with a bit B flipped. Here is the hybrid. Perhaps you guessed that the hybrid is a bit string whose first I bits are output of a PRG on a random seed, and the subsequent bits are just random. Let Pi be the probability that B outputs this fixed flag on such distribution. Now, this probability P, right, is the input is fully random. Oh my God. Okay, you know what? I have to change these slides because I've obviously messed them up. So P minus P prime, this is simply, okay, I just have to switch them. And BS is that. Okay. Okay, so we're back at the same notation as before. So I think I just messed up this line. Sorry, I didn't notice. So so now P is at the outputs of a PRG, and P prime is at random strings. So probability P was at outputs of G. So this is the same as distribution dn, right? Because dn is that the whole string is just outputs of gk. N here is the length of the output of a PRG. It's the length of this random string and the length of this length of the input to B. Now P prime is P0, right? Because if index I is 0, then here I basically none of the bits are formed in this way. All the bits from 1 to n are purely random. Well, that's exactly this distribution, right? And now by triangular inequality, you have a step at which the distance between pi and the next one is at least epsilon over n, right? Because you make, I just assumed for simplicity of notation that p is greater than p prime, right? Okay, again, I didn't say this here. I said it on the previous slide. So let me, what I'm assuming is this. Okay, I just removed the you know the absolute value. Okay, so Pn minus P0 is at least epsilon, so therefore at some point it's epsilon over n. Now, again, because n is polynomial, and I assume that epsilon was not negligible, so that this division is going to be still not negligible, right? So I call this epsilon prime, and it's not negligible. Now, we are not home yet. So di plus 1 is you get I plus first bits that are correct, and then you get random. Di is you get this bit here, the I plus first, is replaced by a random one. That's not exactly what we needed here. What we needed here is that you have, it's almost, but not exactly. Here you have real outputs of a PRG, the first I bits. Here you have perfectly random, but this bit is sometimes correct and sometimes, and in the other case, incorrect. Here I have this bit correct, and here I have this bit random. But basically, a random is an average between correct and incorrect. So a random bit with 1/2 probability is a correct one, and with 1/2 probability is an incorrect one. So this distribution is really it's 1/2 of this one plus sort of the 1/2 of a flip distribution, which looks like this: correct bits here, an incorrect bit here, and random. So the probability of how he does on the di is 1/2 of how he does on di plus 1 and how he does on di plus 1 green prime. That's right, because with this random bit is 1/2 probability looks like this, and 1/2 probability looks like that. So the pi plus 1 is how he does on this wrong probability here. And you can use the triangle inequality, and you can use the exact statement that this probability is just half of these to show that the difference between the red and the green is actually twice epsilon prime. Epsilon was the difference between the red and the black. But that upper bound is also can be argued by just saying that the black is 1/2 of these two. Okay, which I'm saying here. What I wanted is that the difference between the red and the green is at least 2 epsilon prime. So let's walk through it. So pi is the probability of how adversary does on this distribution times the probability that the random bit looks like this, plus the how adversary does on this distribution times the probability that the random bits goes like this. But these two probabilities are 1/2, both of them, right? This probability is 1/2 because it's a random bit. This probability is 1/2 because it's a random bit. So this is just 1/2 the red plus 1/2 the green. Therefore, green is, if you flip this, you move 1/2 to this side, is twice pi minus pi plus 1. So if you subtract, it's a red minus twice the black minus the red. So it's twice red minus twice black. So it's twice epsilon prime. And now we are done, because so the reduction takes, now we have a predictor. The predictor takes first I bits created by the PRG and picks a random bit and a random padding and gives to B this string. And whatever B outputs, if it outputs 1, it's basically a vote that B is correct. So this formula will do it, because this 1 will XOR with a 1, so it's 0. So you actually output the bit B. So this formula simply says, if big guy outputs 1, output the little b. But if the big B output is 0, you are going to output a flip of B. And your advantage is it's epsilon prime, because let's measure what's the probability that this reduction actually outputs the next bit. Okay, so it outputs the next bit if okay, I think I have another typo. The typo is the typo is that here I should have a capital B. So I'm looking at where does this guy output 1 XOR B outputs the proper bit, because that's when A outputs the proper bit. So sorry, just replace this here with a capital B. And if you do, then you will you notice that that basically, so how do you compute this? So do I have this slide? No. It's with 1/2 probability this bit B, because it's picked at random, this bit B is the correct one. So let's look at the probability that this is true for the correct bit. Well, that's a probability that B, sorry, and this is capital B here, on the correct I plus first bits outputs 1. That's precisely this. So it's a red pi plus 1. And now let's condition on this bit, that this bit is wrong. So A, what's the probability that capital B, given a string with the I plus first bit flipped and random, outputs, so the bit was wrong, so this is a 1, so this is a 0. So we're looking at the probability that B on that stuff outputs 0. This stuff is this stuff. So it is the green probability, it's 1 minus the green probability, right? Because the green probability is B outputting on this stuff 1. And this equation works out if B outputs 0. So it's 1 minus pi plus 1. and there is 1/2 in front of each. So you have 1/2 times the red plus 1/2 in brackets 1 minus the green. 1/2 comes in front, 1/2 comes in front, and you have a distance between the red and the green. Okay, should I do this on a paper? Should I do this? Okay, I don't know if I should do this on a paper. Do you have my paper now focused?
Not very focused. Now it's better.
Okay, so okay. So advantage of A in this prediction game on index I of A against the G is the probability. Okay, maybe I should read that. A on the first I bits outputs 1 XOR B XOR capital B of the first I plus I bits, and then B and then random, where B and R are all random. Okay, and so that's what reduction does. Then we know that pi plus 1 minus pi minus plus 1 prime, this was the red and this was the green, is at least 2 epsilon prime, and epsilon prime is non-negligible. And pi plus 1 was the probability that B goes given I plus 1 and the correct I plus 1 bits and random outputs 1 for random bits here. And pi plus 1 prime was the probability that B on first I bit correct, then the I plus first bit flipped, and then random outputs 1 are random. Okay, and now how to tie a divide? And I want to argue that advantage in the prediction experiment of A against the PRG is the probability that B given as 1I and random bit B, because that's what I'm A given this is going to output this. So he feeds him this string, he feeds him a random bit, then he feeds him a random rest of the string. And we want to measure what's the probability that this B outputs actually a correct bit, which is this one. The probability goes right over random R and also random B. So let's condition this. Okay, so first, the probability that B is correct times the probability that B on S1I and correct and random outputs B is correct, so it's just 1, right? Because it's correct, XOR correct, so the XOR out is just 1. Plus the probability B is incorrect, so SI plus first flipped, times probability that B given S from 1 to ith then si plus first flipped, then random, then let's watch. Okay, so if b is bad, then this is 1, right? Because the bad XORed good. So whatever this bit is, this is 1, and this is 1. So this is actually probability that this b outputs 0 in this case, which is intuitive. Like you want there to be the difference between b outputting 1 on a correct bit and b outputting 0 on an incorrect. I mean, okay, no, you want to, you want both. You want to basically, you're using both. You want both of them to average to more than a half, and they do under this assumption. They will average to more than a half. Why? Because so this is 1/2. So this is 1/2. And this, by the way, is also 1/2 because bit is random. So this is what is this? Is pi plus first. And this guy is 1 minus pi plus first prime. Because this is it's the 1 minus the probability that this output was 1. Yeah, because the b, okay, without loss of generality, outputs 1 or 0. And if the probability that he outputs 0 is the 1 minus the probability that he outputs 1. So therefore, this is 1/2 pi plus 1 plus 1/2 1 minus pi plus 1 first prime, right? Which is what I wanted. 1/2 plus 1/2 pi plus 1 minus pi plus 1 prime, which is greater than 1/2 plus 1/2 2 epsilon prime. So it's 1/2 plus epsilon prime. Yeah. Okay. So some, the basic reduction idea, the basic hybrid idea is the same. I mean, whereas before we used the hybrid was over the number of operations of G. Here we have a single operation of G, but what we do is that we fill in some of G's outputs with random bits. We substitute some of G's outputs with random bits. So it's conceptually different. I mean, we are reducing, it's but yet philosophically similar. And the rest is, well, that we have to be somewhat careful with this stuff of like, well, the bit is random or the bit is wrong. So we have sort of cases like correct bit, incorrect bit, random bit. And we have to triangulate properly between them. Okay, do you have questions on how this do you have now the paper or the slides?
I think both.
But which one is bigger?
We can switch them.
Oh, you can switch. Okay, because you're smarter. Like, I cannot switch. I don't know how to switch. Basically, I cannot make one spotlight. No, I don't want to do that. Yeah, basically, I don't know how to switch. Okay, maybe you can tell me on Piazza how to switch, or you can tell me right now.
Just double click your video window.
No, I'm trying. Double clicking, it just doesn't work.
Yeah, I think Oh, you're using Zoom?
Yes.
Are you on the Mac?
No, I'm on a PC. Maybe that's the mistake. I can blame the PC for everything. Okay, so do you have questions on this argument or no? Okay. So I take it no. Okay. My slides fell apart. Okay. You know, maybe with next week we'll start block ciphers, and we will block ciphers, and we'll look at the sort of well, more complex concept of a pseudorandom function as opposed to as just a pseudorandom generator. And we'll look at how they differ, why PRF gives you more power, why we are not done with encryption. So we just saw, okay, you can do a PRG and you have an asynchronous encryption. So now you have a short key, which is a PRG seed, and you can encrypt any amount of storage you want or traffic. So what else do you want? We'll see that there's very apparent, like what else you would like. And just to cut to the chase, you would like to use the same key twice, and you cannot do it with a stream cipher, because the same key implies the same pseudorandom string. So the problems of reusing a key in a stream cipher are exactly the same as the problem of reusing a one-time pad. So you cannot reuse. If you have a stateful stream cipher that takes any message and keeps on having state, and then you guys, why do I need to reuse? I just have a different state. The thing, okay, for example, how would you encrypt a hard drive? You take a key and you derive this huge stream, right? Okay, so far so good. You XOR your hard drive with this. Okay, good. Now the only thing, and now you have the small key, say on a USB stick. So the only thing now you can do is to just regenerate the string and decrypt the whole of that hard drive. But that's not what you want to do. You want to have a random access to a file. You don't want to decrypt everything just to decrypt some file. Of course, you have to decrypt the operating system and some sort of stuff at the beginning. Okay, so far so good. But why do I have to decrypt all my storage in order to decrypt a file? I want to be able to point to some, index very, very far, and I want you to decrypt. And what can a PRF stream cipher do? It would have to regenerate this whole string, work until it gets to that spot. Then it uses it to decrypt. It's linear in how far my blocks are. I want some fast way. Like, I don't want to work on all the fragments. If I want just decrypt a few, I want to work only that much and decrypt them. There's many other applications for basically stream cipher can be used over and over because it's stateful. But you don't want necessarily all your encryption to be stateful. What if it loses state? What if it desynchronized? And so you can check in the book discussions of like how to synchronize stream ciphers, because like you miss a few blocks and you don't know where you are, and you cannot backtrack, right? You cannot go back. in this construction of ours. I mean, that would basically say that it's, if you can go back, that means you're insecure. Oh, by the way, that's a good puzzle. How come it also doesn't imply prediction backward? So let's say you got a chunk of a PRG. How come you cannot predict previous bits? It should be the same argument, but so we'll have many uses for this, but it will be a more complicated thing, the pseudorandom function. But one beautiful thing is that actually, even though it's more complicated, it can be constructed from a PRG. So, and for that, we would need other ways to take a PRG and to reuse its outputs and somehow use it in yet another way. We already seen two, the quadratic longer and longer and longer accumulation, and then the linear small state accumulation. If you learn them, you're like, okay, I can understand them, yes. Okay, now you do the third one. Do the third one. When you see the third one, you'll be like, oh yes, of course. So try to, it's often like this, like you see the thing, you're like, okay, I can understand how it works. If you see a mistake and somebody actually explains why this is a mistake, you can also say, okay, right, I see. But detect a mistake on your own, detect like whether a design is secure or insecure, detect a flaw. And that's much harder. And it's not just harder for you, it's harder for me, it's harder for everyone. I mean, this is a kind of a strange field where like the constructions once shown are beautiful, simple sort of, and convincing, and yet it's not so obvious to see them and to build them and so forth. So as a segue to these constructions of a PRF from a PRG, I will well, the construction will do this. So it will start like this. Let's take that you have a PRG, and we will assume that it's length doubling. So the output is twice longer than the input. It's implied by PRG that takes n bits and outputs n plus c for any constant c, right? Because as we have seen, you can do any polynomial, so therefore in particular you can do this polynomial, right? Like just run this in a loop until you get this output. And now you can, the following thing is still a PRG. So I put an input X into a PRG and I split its outputs, which is, so the input is n bits. And here is n bits and here is n bits. And I take, okay, so it creates an output. And the input was n bits and the output is 2 n bits. But I split it into 2 and I call this x0 and call it x1. And I feed x0 into another instance of this length of this doubling PRG. And I will call the inputs, so this is 2 n bits, x00 and x01. And I will feed x1 into another PRG and call its inputs x10, x11, its outputs. This thing I'm going to call G prime, and G prime took n bits and created 4 n bits. And claim is that G prime is a PRG. And we'll use a tree-based construction for this, where basically we continue this tree. So it's a binary tree of depth 1. But I can stick these trees in here and continue them, right? So the next level is going to have 4 instances, and the output is of size 8n. The next level will have 16n, etc. So this will be a homework exercise. Okay, but intuitively, why this could be secure? Okay, because well, if this is a PRG, then on a random seed, this string is as good as if it was perfectly random. Or no efficient attack can distinguish the string from purely random. Therefore, this x0, x1 is as good as it was just taken at random. And independently, right? Because this is random n bits, this is random n bits. If we replace a PRG with cheat and we just generate this purely at random. So therefore, this string is like a PRG on a random seed. And this string is the same PRG on an independent seed. So that is, if you see what a PRG does, right? If I run a PRG on a random seed, then its outputs are indistinguishable from random. If I run a PRG on a random seed, its outputs are indistinguishable from random. And both of these processes are independent. That's why this whole thing is random. But this is an intuition which you should convert into the kind of argument that we have done so far, right? Which is, okay, some way of showing that this distribution is indistinguishable from some other one, and eventually you have uniform 4n bits, and each step is based by PRG of G. And you can argue at every step by PRGness of G that it must be that these intermediary steps, at the end you want this whole string just simply uniform. At the beginning you have the construction, and it's a limited form of hybrid, right? Like we have seen hybrids where they have n steps. This will just have 3 steps: remove this, remove this, remove this. Okay. Let's see. Okay, it's instructive to see some examples of a flawed PRG extension. So how about that G prime has an input x, and it outputs G of XL concatenated with the XR, and then concatenates that to G of XR XL, where XL and XR is just the parsing of X, right? So in other words, XL is the first half of X, and XR the right half, second half. Okay, so I assume n even, so that right half of the bits are defined. Can we do this? Right, so what would this achieve? I mean, if G takes n bits to 2n bits, then G prime takes n bits and outputs 2n, 4n bits. And it's more efficient than this because it uses G twice on 2 different strings rather than using it 3 times. Does anybody have an intuition like this construction you cannot prove secure? So there is no way that you can prove that any PRG, when performed in this way, will create a PRG. So the claim is for every PRG G, if G a PRG, then G prime PRG, and the claim is false. Because the claim implicitly says that for every G. You could have a PRG that works. No, could you? Yes, you could. So imagine that G does the following. It takes n bits of inputs and actually completely there exists a PRG G such that G prime is a PRG. But it's not true for all. And that's what you, if somebody asks, is this a secure PRG construction? And the following 2 things are true. Okay, so this thing is false. In other words, how do you contradict a universal quantifier? There exists a G such that G is a PRG, but G prime is not. You know what? It's hard. I.e., there exists G such that G is a PRG, but G prime is not a PRG. So you have these 2 facts, fact 1 and fact 2. I'm telling you that these 2 things are facts. I don't explain yet why. That there exists some PRG, if you instantiate this construction, it's going to be secure. That's fact number 2. But there also exists a PRG. You instantiate this construction on that one, and G prime is insecure. Which of these facts is sort of more important? Does anybody have some intuition about that? Like, which of these 2 facts should we take and use? And basically, no. So you know these 2 things. There is some little guy that violates this construction, but there is also some way to instantiate this construction correctly. Which ones would you take as sort of more important?
The fact that it can fail?
Yes, the fact that it can fail. Yes, because basically, like stream cipher works because I don't care what's inside it. Like, as long as it's a little PRG, then I can hook it up by the stream cipher construction, by this iterative PRG in a loop construction, right? Which we called small PRG to large PRG extension. And it will always work, like whatever. So like if somebody wants to upgrade from current cryptography to post-quantum cryptography and instantiate this little PRG with lattices, that's fine. It doesn't matter. We can use it. We don't have to examine the inner workings of this little PRG for the stream cipher construction to always work. This is an example of a construction which, you know, works for some, does not work for others. It's basically a flawed construction. Now, maybe I will show this one. What kind of PRG will make this work? So take PRG G, which on input X ignores the second half of X, but outputs some little inner PRG on XL. So on the first half, where the little inner PRG was very strong. It took half of n bits and outputted 2n bits. We know that from polynomial amount, we can go to any polynomial amount, right? So we have these PRG extensions. So basically the moment, existence of PRG implies that basically you can go from polynomial to any polynomial amounts. This guy will work fine because look, the little inner G in this case, this will go into, it will be G hat on XL, because G hat again ignores the right hand side and just runs, G ignores the right hand side and just runs G hat on the left hand side. So this whole thing will be just G hat on XL concatenated with G hat on the first half, which is in that case equal to XR. But this is fine because this was random n half bits, and this was random n half bits. This is the left half of X, and this is the right half of X. And if X is a random seed, so PRGs, you always just analyze them on random seeds, right? So if X was random, then XL is random and XR, and they are independent. So that's why this, you know, that way you can instantiate it and it's correct. I will put this on a homework. See that there is a way to instantiate this, which does, you know, precisely flip the process opposite of this. Like this construction rescues this one. It does the right thing here, but there is an equivalent construction of a G that shows that if you run it on same bits and, you know, in this way or flipped, then G will actually basically kind of collapse them and will do the same thing. Will do exactly the same thing in this case and in this case, because the inner workings of G is first step, collapse the left and right side, for example. It's not necessary, but this is one of the constructions that will show you that this fails. Okay, like, and therefore on any string of the form AB versus a string BA, it will actually do something very, very similar on these strings, perhaps even identical on these strings. If you come up with an example like this, then this example will contradict this construction, right? What you always need to do when you either contradict something or you show that you can instantiate it, you have to prove that these little things which are sort of weird. They are streamlined exactly so that to either show that this works or that either show that this doesn't. You have to construct them, but you also have to make sure that they are PRGs, right? That this little g must be a PRG. However weird it behaves, either to make this work or to precisely falsify it, you have to do two things. First of all, you want to design it so that it either falsifies or makes true some construction, okay? But also it has to be a PRG. Yes, it must remain a PRG. Now, how can you, how do you, how can I expect you to come up with different PRG designs? Well, the PRG designs, quote unquote, are what we have seen, right? That you can take an output and you XOR it or run on a substring or cut off the outputs and run again on the outputs, etc. Right? I'm not asking for anything more than that. In fact, it's already from this building blocks, you can show that there is a G that violates this, and you can also show that there is a G that satisfies this. Okay? You have the sufficient blocks already in your toy kit.
Professor, I have a question.
Yeah.
Okay, so let's say that instead of using the definition of the PRG, we allow the user to query some at some points the function G. Okay, so he kind of has a Oracle access.
Okay, but
Then
the seed is constant.
Yeah, no, he chooses the seed.
Who chooses?
The user A, let's say.
The attacker.
Yeah, the attacker.
No, then there is no point in querying because then he can run it locally.
Right, but I'm just asking, like, in this context, that couldn't be safe, right? Because you can make XL equals XR, and then
no.
the two parts
What's
the
the
same.
context? The context is that you're accessing some PRG.
No, I'm accessing some function, but I am allowed to choose where I evaluated. But I'm trying to guess if it was chosen randomly to some degree. I'm not sure that makes sense.
No, I didn't get the attack scenario. What I detect somehow intuitively is that it's maybe a simpler thing. That what a PRG security is that PRGs claim to have any good properties only if it ran on a random seed. So misuse of a PRG is in some sense like right here, that these two strings are not independent. And they're not independent in a very sort of simple fashion. I mean, these two strings are also not independent. They came out of a PRG. But there is no test.
Right, they look random.
Their independence. They look random, right? While these guys are immediately testable. If you give me this string and this string, then I can test that they are formed in this way, right? Okay. Very easily. So attacks on PRGs will come whenever PRG is executed on a string that is not really a random seed. Or it's not equivalent to a random seed because it came out of some other process that is cryptographic and assures that the string. So for example, running a PRG on a password, it's a bad idea, right? Passwords don't have sufficient entropy. They have limited entropy. It can be brute force searched, but even worse than that, PRG is not guaranteed to behave any correct way when it's fed inputs that come from very constrained distribution. So because passwords, passwords actually occupy a negligible fraction of the domain, right? So if I take a 2n string, it's a negligible chance that it looks like a password somebody would choose, right? Because it's not even in English, it's not in any language, does not encode correctly, etc. So therefore, a PRG could behave arbitrarily badly. In fact, an algorithm that takes anything that is in ASCII and outputs a 1. So I take a PRG and I special purpose destroy it like this. On all inputs which form English sentences once encoded in ASCII, I mess up the output and I just output like an all 0 string.
Right, because you can change anything that's negligible.
Because I can change inputs on any domain subdomain, which is negligible fraction of the real one, right? And that thing remains a PRG. So therefore, you cannot assume that if you get a PRG, you cannot assume that it acts in any good way, or if it's executed on a subdomain that forms a negligible fraction of the seeds, that we're supposed to. On the other hand, if let's say okay, but maybe this thought experiment, take a seed but fix one of its bits. So fix a bit of a seed, instead of taking a random seed, you fix the first bit. So the first bit is always 1. The rest of the seed is random. They form 1/2 of the domain. Is the PRG guaranteed to have good behavior on those? I'm not going to answer this question. It's a very good question. So I'm going to leave you with this question. I'm going to leave you with this question. Like, you just one bit of the seed is fixed, the rest is random. Half the seeds have this property. Is the PRG guaranteed to have good behavior on such seeds? And by good behavior, I mean, are the outputs of a PRG on such thing supposed to be indistinguishable from random or not? Okay. Any other questions?
Thank you.
Hey. Okay, so I will close now, and good luck with the homework. Oh, somebody asked pi plus 1 and pi plus 1 prime, so that was a long way. Oh, I guess then this person is actually out. Oh no, they're still around. I don't know if I pronounce your name correctly. Huilail? Do you want me to go over that part? Okay. I take it as a no. All right. So see you guys. I will stop recording.